Okay, so recording, we're talking about section 5.1 with a B period here on February 8th. And section 5.1 is called extreme values of functions. So if you see the word extreme, that's exactly what it means. We're looking at high points and low points, and we're using calculus to help us identify high and low points. And this will play a very important role post-session when we start doing more applications of derivative. Unfortunately, we won't be able to see those specific applications until post-session because it just won't quite fit in our 4-week session for this course. But at least I want to lay the foundation here and show you mechanically how do you find high and low points for a function. Now, first off, let's talk about some adjectives here. The word absolute. Some people use the word global, but absolute is what I tend to use. When you're asked to find absolute maximum for a function, you want to find the highest y value within a specified domain. So whatever is the highest point you see, that's your absolute maximum. Likewise, whatever is the lowest point you see in a specified domain, we call it the absolute minimum. So just to kind of do a quick sketch off to the side here, if I were to do some wacky curve like this, right? Actually, let me draw that one more time. Do something a little bit clearer. Say I call this A, and say I call this B. Where is my absolute highest point? It's right here, actually. Even though you see a peak right here, this is my absolute max. Where's my absolute minimum? That's my lowest point. And it's for a specified domain, so it's on a closed interval. Very important. Says closed interval again. More formally, you could say that f is a function with domain with a specific domain D, and usually we use A to B as our domain. Typically use A to B as our domain. Then f of A will be an absolute maximum on your domain if f of A is bigger than any other y value in the domain. So that's what that means. F of A actually, hold on a sec. Let me backtrack a little bit. Let's say A, okay, I was saying our domains from A to B. Let's just keep with that. Then f of, let's say f of C. We'll say f of C would be your highest point if f of C is bigger than any f of X in your domain. And we'll say f of D would be your lowest point if f of D is less than any other y value in your domain. Sorry, that was a little confusing. A to B, I made the endpoints of the domain. I'll stick with that. Let's talk about example 1 now. And here we have 4 different graphs. Actually, the 4 identical graphs, but 4 different domains. So we see here that your domain is all real numbers. So you're going to draw little arrows, and the whole thing's covered here. This domain is from 0 to 2, and they have endpoints that are closed. So you have that. This is from 0 to 2, so 0 is open, 2 is closed. And here, these are both open. Okay. So do I have an absolute maximum here? No, I don't. I don't know what the high point is on that first graph off to the left. It goes up forever. Okay, I don't know what the absolute maximum is. Do I know the absolute minimum? I do. And it's 0. And by the way, you're always going to state the y coordinate when you're given absolute maximum value. You don't state the x coordinate, you typically state the y value. You could say that the absolute minimum is at 0, 0, or when x is 0, we have an absolute minimum at y equals 0. But typically, you just state just the y value or y coordinate. Now, here I have a closed one from 0 to 2. Do I know the absolute maximum? I do. The highest y value here is 4. The lowest y value, of course, is 0. And that's it. Now here I have a semi-open or semi-closed interval. 0 is not included, but 2 is included. Do I have an absolute max? Absolutely. 2. Do I have an absolute minimum? I don't really, because I don't know how low. I mean, I know it's getting close to 0 for y, but I don't really know what it is. Like, is it 0.00000001? I don't really know. And then likewise here, I'm going to say no and no. because this is an open interval, I don't really know what the highest value. I know it gets close to 4, but I can't really say with confidence exactly what it is, and that's a problem. Absolute maximum is 4 for the third graph. Oh, yes, sorry. My bad. I gave the X value. My apologies. Thank you for correcting me, Vita and Catherine. Thank you for correcting me there. I appreciate it. Yes, there was an absolute maximum. It is 4 on the third graph. Sorry, just getting too caught up with explaining the other stuff here. Okay, so what has to be true if you want to guarantee both an absolute max and absolute min? You are going to need a closed interval, just like we saw in the second graph. You are going to need a closed interval, from like, A to B. What else do you think we would need? We will need, it's not quite clear yet, but I'm going to talk about it in just a second. You will need continuity. You might remember that from last semester. Continuity is a big deal. So consider the function down below. It is a closed interval from 0 to 6, so it's closed, great. But not continuous. So can I find absolute maximum? Not really. So we start here, we end here, and this goes very close to 4, but not exactly 4. Gets really close to 4, and then you have this, and you have a jump. This is actually a jump discontinuity. So the answer is no. We do not have an absolute maximum because we were not continuous. So you have to be continuous to guarantee both an absolute max and absolute min. So this leads me to a very important theorem that we will talk about often this week, called the extreme. Actually, we'll talk about it throughout this whole 4-week session. Extreme value theorem. I call it EVT for short. EVT. If f is continuous on a closed interval, then f has both a maximum and a minimum. And when you say maximum and minimum, you assume the word absolute. If someone doesn't say absolute, like, what is a minimum, what is a maximum, assume they mean that. So it's just assumed. If you don't, if it's not mentioned, just so you know. Assume absolute if not mentioned. Any questions about the first page before we move on to page 2? Okay, so again, note that we use extreme value as a blanket description for max and min values. I just described it. If you don't see it, you just kind of sorry, if you don't see the word absolute, you assume the highest and lowest point. But we have to get a little more detailed here sometimes, because there are also things called local extreme or relative extreme values. Local and relative mean the same thing, just so you know. It's just some people like to say local, some people like to say relative. I kind of use both interchangeably. So there's also something called a local / relative min or max. What does that mean? Well, before I get too deep into it, it'll make more sense later this week, because we're going to have a very specific discussion about local max and min values. But let's talk about home prices, for example. Say you want to find the the absolute most expensive house in San Mateo County. You're probably gonna be looking at Atherton or Hillsborough, right? Maybe the house that Steph Curry. Well, I think there's homes more expensive than Steph Curry of the Warriors. But he paid I think 30-40 million for his house. But like you would look all throughout San Mateo County and you say, okay, let's find the most expensive house. But what if you just wanted to say, well, let's just look at maybe Redwood City, or maybe a certain neighborhood in Redwood City, like Mount Carmel or Edgewood, or maybe just in your in your neighborhood, like maybe in a 1 mile radius. In that case, you would call that a local maximum, right? Like, locally, this is the most expensive house, even though there are more expensive houses within my county or within my, the Bay Area. You're kind of just looking at a very specific region when you talk about local. So, for example, this right here, I would call a local max. And this right here, I would call a local min. But here, because this looks like the absolute lowest point, I would call this an absolute min. This right here, I would call actually an absolute max because that looks like the highest possible point.
So Mr. Amashi.
Yeah, go ahead.
Could you have like multiple local
Absolutely.
minimums and
yep.
and maximums?
Yep. You could
Cool.
have a curve that does like a sine curve. That's a great example.
Gotcha.
Or if it is something funky like this, totally. But see, these all here are all going to be locals, and these are local mins, because there's really no absolute min, there's no absolute max because we don't have this closed, right? It's not a closed interval. This right here, actually, we would call a local min. It's a little confusing. I'll explain that. I think by tomorrow we'll have a discussion on that. So, but endpoints could be local mins or maxes. That's possible. By the way, a point could be both absolute and local. So to answer this question, will absolute max also be considered a local max? Yes, it would be. So this is absolute max and a local max. Absolute max is like an extra designation. It's kind of like, I'll use like maybe, I don't know, I'm trying to think if using a sports analogy to make much sense. Well, let's use maybe like CCS. I think it might be a little more appropriate because a lot of people here play sports for our school. But like, say for example, you make first team water polo, right, or first team football, and then all of a sudden you make first team in the state of California, or first team All-American. If you're going to be first state in California, I mean first team in the state, or like one of the top players in California, one of the top players in the United States, you're probably going to be a top in CCS also, I'd assume. So it's just like an extra, when you're an absolute, it's like an extra designation. So absolute maxes are local maxes, absolute mins are local mins, just so you know. And then there's kind of a formal language, which might be a little confusing, but they're saying f of c is a local max if f of c is greater than f of x for some open interval containing c. So like if I had an open interval here, then I consider that to be, a local max. Or if you just made a random point x equals d, then your local min, as long as this value is lower than any other y value in some neighborhood. So that's kind of what's being mentioned there. Again, if it seems a little confusing, don't worry. It will all be cleared up by tomorrow, just so you know. So just be patient, just trust the process. This actually, I don't like this stuff. This seems just weird to me. So I'm gonna actually just cross this off. I didn't really talk about it the last session and it didn't really matter. So it seems kind of confusing and I don't wanna get you guys in circles. I want you guys to start doing some practice problems in a little bit. So let's just chop that off. Let's move on to page 3. Okay, so let's revisit what we just talked about in example 2 here. Can we articulate where local extreme values will happen? They seem like that will happen at endpoints of your domain, or your interval. And it seems that it'll happen where f prime equals 0, meaning you have a horizontal tangent. So that's f prime, by the way. Or where f prime does not exist. That usually happens when you have like a corner or a cusp. You might remember that stuff before. So let's take a look at this graph again. I definitely had a horizontal tangent right here. I definitely had a horizontal tangent right here. And that's a cusp right there because the left-hand derivative and right-hand derivative don't equal each other there. You might remember that from the fall. So we still have to reinforce all these old things we did in the past. And of course, these are endpoints right here. So that's where we are seeing these extreme values happen at those locations, either endpoints or wherever f prime equals 0 or f prime does not exist. By the way, when f, oh goodness. By the way, when f prime does not exist, or f prime, whenever f prime equals 0 or does not exist, we call those critical points. And we use that term often during the session. They're called critical points, where f prime equals 0 or f prime does not exist. And we're going to find those analytically just a little bit. Also keep in mind that I know it's a little bit hidden here, but could you have a local extreme value at a point C in the interior of the domain where f prime of C is positive or f prime of C is negative? The answer is no. We cannot. Your derivative has to be 0 or does not exist for you to have a local extreme value. Because if your derivative is positive, then it's just gonna be rising. Like if your derivative is positive here, right? Like, you know, let's say I call it like point A, or we'll call it point C, just to be consistent with the notation there. Obviously, that's not an extreme value. I have a positive tangent line there, right? I have a positive derivative. Or likewise, if I had something that was negative for the slope of the tangent line, well, yeah, that's not gonna be an extreme value. Like if I have a curve that does this, and so like say I call it point C, and I have a negative tangent line there, that's not an extreme value. So your derivative has to be 0 or does not exist, or you have to have an endpoint of a closed interval for you to have local extreme values. So in a question. Nope. A critical point again is defined when f prime equals 0 does not exist. So it's defined there as well. And this is kind of a big deal, the one you see in box and bold. Extreme values, local or absolute, only occur at endpoints or critical points. So those are the two places we've got to look. Now, a little bit more some theory, I guess, some abstract stuff, just a little bit, and then we'll do an example. And then maybe after example, I think we'll see if maybe we'll do a little break and come back and do another example, and then we'll do the worksheet after that. But we're humming along nicely here. So now let's look at this question. Is it possible to have f prime equals 0 and to not, I emphasize the word not, to not have a local max or a local min? Likewise, is it possible for f prime to not exist and also not to have a local max or local min? Well, let's see what's happening here. That's a horizontal tangent. F prime equals 0 here for sure. That's a horizontal tangent. F prime equals 0 there as well. That's a vertical tangent. F prime does not exist here. That's a cusp, which, you know, is kind of weird, but F prime does not exist there as well, because the left and right hand derivatives are not the same. Now, here I have a local max. Duh, it's right there. Here I have a local max for the fourth graph, right there. However, there are no extrema. Extrema, by the way, is the plural of extreme. We don't say extremes. That's actually poor grammar. So extrema, or instead of saying minimum, you know, like if you have more than one minimum or more than one maximum, you don't say minimums or maximums. You say minima and maxima, just so you know. Sounds kind of cool, actually, when you say that. So what we're noticing is that just because f prime equals 0 or f prime does not exist, does not guarantee an extreme value. Does not guarantee an extreme value, but it could happen. Now, extreme values for sure are going to be located at where f prime is equals 0 or does not exist, or endpoints within your closed interval on a continuous function. But it may not. But you could have a whole bunch of places where f prime equals 0, and it may not be true. But it is a necessary condition if you want to be an extreme value that you have to have either an endpoint or a critical point. Remember, critical points where derivative does not equal 0. Yes, great question, Vita. Great question. Is this true for all real numbers? Yes. Yeah, what we're noticing here is our domain was all real numbers. So we're not closed. Not closed interval. So that's just something to keep in mind. So it's not necessarily a guarantee. And how do you know? Like, then how would you be able to find f prime equals 0? But how can I tell? You can look at the graph, obviously, but there's also another technique that you'll learn tomorrow that will help you analyze these graphs even further without the need to graph it, where you use calculus skills. But for now, let's just focus on finding the absolute min and max. We'll do local extreme values more so tomorrow and Thursday. Okay, so now let's move on to an example. I'm going to spend a good amount of time here, and then if we get to 210 after this example, then we'll take a break. We'll come back at 220, and then we'll do example 5. And then after example 5, then we'll do a breakout session. So here, example 4, you're asked to use analytical methods to find the extreme values of the function. Now, let me lay out the steps here, because some of my students actually kind of botched these steps the previous session, and I don't want that to happen for you guys. Let me lay out the steps here first, and then we'll do it. So here are the steps. I'm going to type it up first, and then you'll see. Hold on, still typing, guys. Hold on. Oh, goodness. Almost done here, guys. Just be patient. Okay, let me expand this to, okay. Okay, there we go. So feel free to take a picture if you want. I am recording this, so you guys will have the recording. Or just jot it down. These are the steps. It's somewhat labor intensive, but it's not that bad once you get the hang of it. And I do reinforce this just so you know over the next 4 weeks. So you will get better with this. But there is a formality that we should follow. First of all, you got to check see if the extreme value theorem applies, because I just showed you some examples where if you're not closed or you're not continuous, then we didn't have necessarily absolute mins or maxes. So you got to check to make sure if it doesn't apply, then you stop. You don't even do the problem. Or maybe you can just kind of look at the graph and tell me, okay, well then I guess there's no absolute max, but there's an absolute min here. I'm not gonna do that to you guys though. I am gonna give you something that where the theorem will apply, but you got to state it though. You still got to state it. So how do you check to see if it applies? Make sure you're continuous on a closed interval. How do you know if it's continuous? Graph. And closed, duh, it's closed. That's closed. That's pretty obvious because it equals 1 and 4. How do you tell if it's continuous? How do you know? From a graph. And you can use Desmos or a TI4 calculator, I don't really care. So you can just do a quick little sketch, So, okay, here's a little sketch. Mr. E says from 1 to 4, inclusive, closed, continuous. It applies. Make that statement. If you don't make that statement, you will lose points on your test, just so you know. So you gotta make that statement. Even on the AP exam, they do that as well. And again, even if you're not doing AP, I have to treat this class like it to maintain the standards and the rigor. Now, number 2, find the derivative set equal to 0. Okay, that's easy. And solve for x, fine. That's gonna be your critical point. That's where f prime equals 0. Also see if there are any other x values where f prime may not exist. Again, that's also a critical point. Once you've done that, now make an xy table and you test the endpoints and the critical points to see which one has the highest y value and the lowest y value. When you test it, you're going to plug into f of x, the original function. You want to see which x coordinate gives the highest y value for the original function and the lowest y value for the original function. And so when you're testing the x coordinates, of both the endpoints and the critical points into the original function. And then you make a formal statement at the end. I'll show you how to write that when we follow through on this problem. But these are the 4 steps. Let me do this in blue for a bit of contrast. And I'll kind of keep the stuff here in red. So what you'd first say is that since f of x is continuous on 1 to 4, and obviously you're making it closed, so it's implied just a closed interval, then EVT applies. That's the first thing you gotta say. So that's step 1. Check. Step 2, take your derivative. Now, if you're a little rusty, that's okay. Remember, you can rewrite f of x as 4x negative 1 plus natural log of x squared, by the way. So when you do that, you're just going to do this. You're going to do f prime of x equals negative 4 times x to the negative 2 power plus, now it's ln, so you have to do 1 over x squared, and you got to do a chain rule times 2x. In case you guys forgot chain rule, you got to do that. If you so desire, remember ln x squared is 2 times ln x. That's like a property of logs. And then you can take derivative ln x as 1 over x, and you get 2 over x. You get the same thing if you clean it up here too. If I clean it up, I get negative 4 over x squared plus 2 over x. And we're going to set this equal to 0. Now, any questions so far about the derivative part? And again, if you're a little rusty, look at your old notes. Actually, if you still have access to my YouTube channel, you can look at all that stuff too. Now, we got to solve for x. This is where there's some algebra coming into play here. By the way, f prime does not exist. At x equals 0, because obviously you can't divide by 0. But I don't really care about that. Actually, I'm not even going to consider it. Why am I not going to consider x equals 0, even though the derivative does not exist there?
Because it's not in the domain.
Not in the domain, perfect, right. We're only interested from 1 to 4 and anything in between. So, right, I mean 1 to 4 and anything in between, right? So I'm not going to really consider that because it's not in our domain or our neighborhood, right? But the rest I will work out. I'll probably move the 4x squared to the other side. I will cross multiply. I'll move everything over to one side. I'll do some factoring. And I see that x is going to equal 0 or 2. Again, we're going to ignore 0, but keep 2. So now we have my critical point. So check that off. Okay, that's where you're really going to spend most of your time, just so you know. Step 2. Any questions how I found that? Nope, okay. So we're going to do another one of these, and you're going to do some practice problems. The worksheet number 1 for this class, I believe there are 3 examples. So you're going to have a chance to practice this too in breakout sessions. Don't worry. Okay, step 3. I'll do it over here. Make an XY table. Fantastic, XY table. You're going to test your endpoints, which are 1 and 4, and your critical point, which is 2. You're going to test those x coordinates into the original function. Let's plug 1 into my original function here. Let me erase some stuff here. I don't need like all this junk anymore now. Oh my goodness, what did I just do? Undo, 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 undo. There we go, okay. Oh goodness. Okay. All right, anyway, let's plug 1 in. If I plug 1 in, 4 over 1 plus natural log of 1. Log of 1, any base, is 0. So that's just 4. Let's plug 4 in. You're doing 4 over 4, which is 1, plus natural log of 16, which is a pretty big number. Okay. Actually, if you want to know what it is, it's 3.77. Sorry, if you add it all together, natural log of 16, I think, is 2.77. Yeah. So it's let me put it in parentheses so it's not confusing. So that's 3.77. And if I plug 2 in, it's 2 plus natural log of 4. And that's going to be 3.38 to work that out. So it's pretty clear that this, so we can check that off, that's done. That is my absolute max. And that is my absolute min. Okay. That should be very clear. So now let's make a formal statement, and then we'll do a breakout for that. I'll do the form say up here, and I'll do it in green. So you'd say that f of x has an absolute max of 4 at x equals 1 and an absolute min of 3.38 at x equals 2. Okay. Let me move that so you guys see a little better. So you see I have it in green here. Fx is absolute max of 4 at x equals 1 and absolute of 3.3 at x equals 2. Not that hard to write, but that's considered AP style language. I'm going to care even more about that when we get to 5.2 and 5.3. It's going to be even more, no pun intended, more critical. Actually, that was intended to say that. They do care, when I say they, the College Board, how you write that. And now they know, we know that the AP exam is going to be like, I think they've released the format. I'm pretty sure it's going to be free response and multiple choice, and it's going to be in person or online. So they're going to have this kind of stuff. So anyway, that's how you do this problem. Let's do a 10-minute break. It's 2:14. We'll come back at 2:25. How about that? So 10 minutes and some change. We'll come back at 2:25. We will do example 5 here. We'll do a little more quickly now, and then you'll do some problems in the worksheet for about 20 minutes, and then we'll debrief at the end. And homework's gonna be just like this stuff. So hopefully this is kind of easing you back in the swing of things, and it's not too crazy. So I will clear, and I'll just pause the recording and pick it up. Recording, sorry. Okay, resume recording. Okay, so we're back. Example 5 of the section 5.1 notes, last page here. So we graphed x equals to, we graphed f of x equals x to 2/3 power. We saw those continuous. So you can make your statement, f of x is continuous on the interval from -1 to 2. So EVT applies. And how you exactly say it, I don't really care. You could say EVT applies because f of x is continuous on a closed interval -1 to 2. Or you can start by saying f of x is continuous on the closed interval -1 to 2 because EVT applies. I'm not going to really care too much about that, but make sure you tell me the continuity in the closed interval part and that EVT applies. Make sure you tell me that. Okay. Then let's take the derivative. That's easy. 2/3 times x and -1/3 using the power rule, right? Using the power rule. Set it equal to 0. So 0 equals 2/3 times the cube root of x. So remember, that's a negative exponent, and it's a radical because it's 1/3. Now, f prime does not exist at x equals 0, and that's just kind of by inspection. And we are going to have to consider that because that is in our domain from -1 to 2. So that's really more by inspection. Like you just have to, and how do you know when something does not exist? Look for x in a denominator. That's usually what you want to do. So you got that there. You cross multiply. So you get 8/27. Remember, you had to cube both sides. So what I did is I multiply both sides by 3 times cube root of x to the others. Oh, wait one sec. Wait. Oh my goodness. I can't believe I did this. Okay, I made a big mistake, guys. What mistake did I make? Anyone see what I just did wrong?
There's a 0 on the left.
Yeah, it's not 1. That was a 1 there. Oh my goodness. Okay. See, I'm human, but I caught myself because I was like, wait one sec. If I put 8/27, it does not to be 0. Yeah. So in this case, so definitely we have this as a critical point. Definitely have our endpoints. The problem is that this can't equal 0 because your numerator is stuck at 2. In order for a fraction to be 0, the numerator has to be 0. So yeah. But 0 makes it undefined, so we'll use that as a critical point. So now I make a table. -1 and 2 is my endpoints. 0, that was what made the derivative undefined. Now I plug -1 into the original function here. -1 raised to the 2/3 power. You got to square the -1, so it becomes 1 cubed root, it's still 1. 2, that's going to be the cube root of 4, if you were to work that out. Which I think is, hold on a sec here. 1.587 roughly. 1.587. And then if you plug 0, you get 0. So it's pretty clear that my highest value is 1.587, my lowest value is 0. And that was actually a cusp. We saw that, and it was undefined, or so the derivative is not defined at a cusp, because the left and right hand derivatives don't equal each other, as we discussed in the fall. So when you make your statement, you make a statement like this. You would just say, f of x has an absolute max of 1.587 at x equals 2. Also, you would say f of x has an absolute min of 0 at x equals 0. And there you go. Any questions on this one? Question in the chat, yes. Oh, no, no, it is defined at 0. The derivative was not defined at 0. 0 is defined for the original function. The original function, 0 would be defined here. Remember, you want to find where x is, you want to find where f prime is not defined, right? Because that's a critical point. Remember, the graph looked like this. Now, if x equals 0 is not defined for the original function, then sure, then you ignore it. But 0 is defined for the original, not for the derivative, and that's okay. That's okay. We hopefully that makes sense. So again, you're trying to find where the derivative is not defined. How do you pick the x value in the t-charts? Oh, you just pick the endpoints, -1 and 2, right, are your endpoints. And you pick your critical point, which is 0. And how do you find your critical points again? Set derivative equals 0 and solve for x. We couldn't solve for x when we set derivative equals 0 because your numerator is stuck at 2. However, we saw that 0 made the derivative undefined by inspection. And again, it's okay for your derivative to not be defined as long as it's defined for the original function. And you can use that to test into the original function. That's totally okay. Because it could be an absolute min or max. So, and by the way, sometimes your critical points could have, you know, they could be decimals, or I mean, we solve for. I mean, I could have chosen an endpoint that was not an integer. It doesn't have to be whole numbers. Let's look at this one more time. Let's look at the worksheet. The worksheet kind of lays it all out. So this is worksheet 1, which you can download in Schoology. Number 1 is like write out the extreme value theorem. We know what it is now. It's actually in your notes, right? The extreme value theorem is on the first page near the bottom. If f is continuous on a closed interval, a to b, then f has a maximum on the interval. So you don't have to write that out, that's fine. But we know what it is now. For problems 2 through 4, here are the steps, and the same steps I mentioned earlier. State that f is continuous on a closed interval and therefore EVT applies. Step 2, find your critical points by finding the derivative, setting it equal to 0, or see where f prime does not exist. Anything that's not, any critical points are not in a given interval, toss it. Like we actually did for example 4, we tossed one of those out. If there are no critical points, then state that they don't exist. That's fine. Just state that. Then you're gonna test your endpoints, A and B, we'll call the endpoints. C1, C2, and so on are the critical points. Test them to the original function and see what the Y values are. Anything that's highest is an absolute max. Anything that's lowest is an absolute min. You make a statement at the end about that. So those are the 4 steps. So you guys have now 3 separate equations to work out here, functions. X squared minus 8 times ln x, 4/3 x minus x to the 4/3 power, and x to the 3 minus 3x squared plus 1. And you do have closed intervals, 1 to e for the first one, for number 2, -1 to 8 for number 3, -1 to 4 for number 4. All the same instructions, state the EVT applies. I mean, yes, I'll tell you, they're all closed intervals. I mean, they're all continuous and closed intervals, but just say that it applies, make a quick statement about that, find the derivative, set it equal to 0, solve for x, also see if there's anything where the derivative will not exist, and x values, test them into the original function, your critical points and endpoints, make your statement, which one's highest, which one's lowest. I believe I have the answer key for this in school, so you could check your work. Excuse me. So if you click on week 1, lecture notes and worksheets, and you should see it right there. And actually, I may even have it in my Dropbox. So just show it to you very quickly. Yeah, there we go. And fortunately, I didn't have to make this from scratch. It's from Mrs. Blanford from many years back. But yeah, you can see it's all laid out right there. So let's do this for 15 minutes. We'll do in a breakout session. You might be able to do each one in 5 minutes. If you don't finish it, that's okay too. Or you can divide and conquer. I'm gonna put you guys about at least three people in each breakout group. So if you have questions, call me over. Ms. Walker already left. She doesn't really stay here for all the classes. Just so you know, I don't have exclusive right. Oh, actually, let me stop sharing.